A large solar panel capable of being deployed and retracted in space can be a reality through the use of an unique solar panel design concept developed by Ryan Aeronautical Company of San Diego. In bestowed position, ready for launch, the Ryan array is wrapped tightly around a lightweight metal drum, compact, small volume. In space, it extends a large, flexible solar cell area. Lightweight materials have been selected for optimum weight-to-power ratio. The storage drum is fabricated of magnesium with aluminum honeycomb end plates. Solar cell substrate support beams are of thin-gauge titanium. The substrate is not a metal at all, but a thin sheet of fiberglass or kapton. Power is carried from the solar cell modules by wires that are bonded to the substrate and routed along its edge to a connector that passes the current into the spacecraft via a spirally wound, flat-spring electrical harness. Thus, maximum power is available from the panel for use by spacecraft electrical systems. Except when deploying or retracting, the panel uses no power itself. When it does use power, consumption is low. In the case of this prototype panel, about 7.5 watts to extend and about 10 watts to retract in a 1G field. Because of the extreme simplicity in the Ryan design and the thorough trade-off studies and analysis of various concepts, materials, and processes required for successful operation in space, Ryan can assure high reliability for its concept of a large retractable solar cell array. Ryan's methods have been established through developmental contracts with the Jet Propulsion Laboratory, funded by the National Aeronautics and Space Administration. Through these contracts, Ryan has achieved significant breakthroughs in this specialized field. This array was Ryan's first, approximately 3 feet wide and 18.5 feet long, a 50-square-foot proof-of-principle rollout solar array. Work began in April 1965. Hypothetical structural and environmental requirements were established similar to a 1969 Mars launch by an Atlas Centaur with a Surveyor-class shroud. Environmental testing of the array continues today. This initial 50-square-foot array furnishes 14.5 watts of electrical power per pound, using present-day solar cell installation weight of 0.18 pounds per square foot. A second contract was awarded by JPL in June 1967. Ryan designers expanded their concept to a 250-square-foot array, 5 times as large as the prototype, one capable of producing in excess of 30 watts of electrical power per pound. Phase 1 final report on this contract is due in June 1968. Ryan experience in solar panel design and fabrication spans more than 8 years. More than 350 panels have been delivered. Principal programs were Mariner, with successful flybys of Mars and Venus; Ranger, with 4 successful lunar photography missions; and Transit, the Navy navigation satellite, which began in 1962 and is a continuing priority program. Ryan panels were also on the GEOS and DOD satellites. Experience in space electronics includes the landing radars for the Surveyor unmanned robot, 5 of which soft landed successfully on the moon, guided by Ryan radar. Production of the sophisticated Ryan landing radar on the Apollo lunar module, which will assist American astronauts in landing safely on the moon before the end of 1969, has given greater depth to Ryan's ability to design, package, and test electronic systems that will survive in space. Also, a Ryan high-altitude altimeter was used in the development of the Saturn launch vehicle. It exceeded specifications, measuring to 1% accuracy out to altitudes above 300 miles. 3 aspects of Ryan's rollout solar array concept are unique: the support beam, the deployment mechanism, and the substrate. Each aspect contributes to the space readiness of the concept. First is the uniquely conceived extendable beams. It is made of two narrow strips of titanium, seam welded at the outer edges and heat formed. This forming retains an elastic memory in the beam, giving it a tubular shape that resists bending and torsion. This unique elastic memory permits flattening the beam and wrapping it around the drum. In this compressed position, the beams are only 12 thousandths of an inch thick per layer. On command, the beam extends rigidly straight up and can be retracted if necessary for docking and mid-course maneuvers, or in zones of high radiation, such as the Van Allen belts, where sensitive solar cells will need protection. A natural oxide is formed on the surfaces, both inside and outside of the titanium support beam during the heat annealing process. This oxide acts both as a thermal coating and prevents metal-to-metal adhesion in the vacuum of space. Additionally, titanium offers an optimum modulus-to-weight ratio, resists corrosion, and is non-magnetic. An added feature of the titanium structural members can be illustrated with this 1/4 scale model of the 250 square foot array that Ryan is building for JPL. Should the array experience excessive G loads during orbit, the panels would not be damaged, but would fold, and when commanded to retract, would straighten out automatically, to be deployed again to continue its useful mission. Another aspect is the rollout mechanism itself. In the prototype 50 square foot array, each hub of the stowage drum was equipped with spring-loaded rollers. The rollers hold the titanium support beam tightly against the main body of the drum. To guide the support beam as it feeds off and on the drum during deployment or retraction, Ryan engineers built special Teflon-lined guide sleeves. These units react to the loads imposed by the beam at full extension and follow the changing radial distance from the drum centerline of the beam as successive layers are added or removed from the drum. A 24-volt DC, 12,000 RPM motor with an integral planetary gear powered the prototype array, taking about 4 minutes to deploy fully. A 5-tumbler limit switch mechanism governed the rate of deployment and limited maximum in and out positions. Ryan's rollout technique has evolved to this stage now, as demonstrated on the 1/4 scale model. Instead of the spring-loaded rollers, a spring coil principle is used. The titanium beam is compressed and held tightly to the drum by tension springs at each end of the drum. Silicon rubber teeth have been added to the center crown of the support beams to demonstrate a rack and pinion type drive that deploys and retracts the array. Actual spaceflight models will have a corrugated titanium strip welded to the beam in place of the rubber teeth. Purpose is to control the movements of the beams more positively. Also, the guide sleeve has been greatly simplified. It is now one solid part, machined from a block of Teflon. Each of these changes is a logical step in an evolutionary design. Full-scale model of this array, 7.5 feet by 46 feet, is now in fabrication for JPL. The third unique aspect of Ryan's array concerns the substrate. In the 50 square foot prototype, Ryan chose a fiberglass cloth that was impregnated with resin. The sheets were 3 mils thick and divided into separate segments to simplify installation, test, and repair of the solar cells. The substrate segments were hinged together with a fiberglass pin and attached to the titanium support beams with lightweight metal clips. Based on this technology, Ryan selected a new material, DuPont Kapton, for the substrate on the 250 square foot array, and proposes to use this hardy 1 mil thick material on future deployable arrays. On the other side of the substrate from the solar cells, Ryan engineers placed Teflon-coated silicon rubber spaces that provide a frictionless cushion between the layers of the substrate when it is wrapped around the storage drum. Ryan's rollout array is a functional concept. It is a method that can provide larger solar cell areas than has previously been possible. But it is more than an idea. Hardware has been built and is being environmentally tested. Ryan's array has been subjected to a vigorous space environment testing program, including deployment dynamics, launch vibration, solar electrical reliability, and thermal vacuum. Purpose of the deployment dynamics tests was to determine the natural frequency of the array, to verify that the array will not resonate at the same frequency as the guidance and control system during spacecraft orientation maneuvers. Vibration tests simulated the shaking that the stowed panel might experience during launch of the rocket booster. Sinusoidal excitations built up to 4G levels between 20 and 200 hertz. Induced load at the end bulkheads reached nearly 200 pounds. Tested next was the degree of free or non-tension substrate wrap of the panel. Ryan analysts determined that a tensioned wrap on the stowed panel is not as essential as is the compactness of the panel as it is wrapped around the drum. Accelerations grow more severe as vibration levels sweep from 5 to 20 hertz at 1.6 G and from 20 to 200 hertz at 4 Gs. The tests confirmed that free tensioning of the substrate is not required. In full sunlight, the array was tested for electrical performance after each vibration test. The array was extended and retracted a number of times, while technicians recorded electrical output data. Thorough vacuum and solar thermal tests are now being conducted, in which the panel is being deployed and retracted in the simulated environment of space. Ryan, a company with the necessary background of experience in the design, fabrication, and test of spaceflight hardware, ready for the challenge of placing a large retractable solar cell array in space.